In this video, I'll be introducing the definite integral. So we've been talking about Riemann sums, and while this formula here can look quite intimidating, there's a lot going on. Basically, the definite integral is saying that it's just equal to the limit of Riemann sums as the rectangles get smaller and smaller. So n is the number of rectangles, and we're looking at the area of all of those rectangles. We're taking, it doesn't really matter if we're taking the left endpoint or the right endpoint or the midpoint, as long as the function is continuous, so as long as this limit exists. We're just looking at the area of the rectangles, and then we're taking more and more rectangles. So basically, what this is saying is that this integral from a to b of f of x dx is equal to the area under the curve between x equals a and x equals b. Okay, so what does that mean? Well, let me draw you a picture. So let's say we have a curve that looks like this. And over here, I have the point x equals a, and then over here, I have this point x equals b. And this integral will be whatever area is between the x-axis and the curve. So it's bounded above by this curve. Okay, so when we say area under the curve, that's what we mean. So one question you might have is, well, what happens if the curve goes below the x-axis? Okay, so let's see an example like that. Maybe instead our curve looks like this. Okay, so what is the integral measuring? Well, again, the integral here from a to b of f of x dx will be measuring this area between the curve and the x-axis. Up here, with our first example, this will end up being positive area. Down here, if it's below the x-axis, the integral will end up being negative. So basically, any area below the x-axis is considered to be negative area. Okay. So if in particular we had a function that did both, and let's say we went from a to b, and for convenience, let's call this middle point C. If this area is A1, and this area is measured to be A2, in sort of a positive sense, then what this integral does from A to B is it's basically like thinking of the area A1 and then subtracting that area A2. If you're thinking of A2 as being a positive number, a positive area, right? You're subtracting it. Now, integrals work just like area. You can separate it into pieces. So another aspect that we get, another property, is that this integral is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And so that can be convenient to split an integral into two pieces and then add them up. One more property that you'll see show up again and again is that if you are taking the integral from a to b of a function, what you can do is you can also kind of flip these limits of integration. And what happens there is the integral becomes negative. Okay, so what you should think about is you should sort of think about like going backwards. So when you're looking at it going backwards, it becomes negative. Okay, and that will be another useful property. The last one I want to mention is to think about if you had sort of a function here, let's call that f of x, and then that gets multiplied by some value. So maybe up here we have k times f of x. So by some constant k. Then if you want to integrate from one point to another of this new function, k f of x, right, that would be sort of this area. What you can think about doing is taking that blue area and then multiplying it by k. So in this case, I don't know, k is maybe about 3, right? So we can see that blue area showing up here and here. Okay, so just kind of like when we're taking derivatives, we can pull constants out in front when they're being multiplied. And that will also help simplify a few problems for you.